Uh, so let's resume the last lecture. I last proved the most important result, in my opinion, regarding the method, which is basically the following property. It's the relation between unfolded sequences, unfolded functions, and the original domain. So it's like this. So recall that this is our thin domain with rough boundary. This is the, let's put a little bit more. So we have basically the cell sometimes here, and this remaining, let's say like this, is what is this R1 epsilon. There are some few remarks we might do regarding this, I believe, most important properties. So the first one is like this. So notice that since we have this order of compression being epsilon, somehow we had to correct with this 1 over epsilon. So it makes sense for us to consider, say, LP norms and Sobolev norms. I will consider Sobolev norms and as well LP norms as this. So as the classical norm, where this X is LP or X is a Sobolev space, okay? I won't mention the L infinity, but when we have the L infinity, there will be no correction term due to the characteristic of the norm. Moreover, once we look at this property, there is something that we might be concerned about, which is this integration defect, yeah? So it's the integration defect. Why? Because, I mean, it's somehow a strange term that appears in the relation between the integral over the domain, original domain, and the unfolded domain. So, but, I mean, we actually can prove that this integration defect will converge to 0. I will just state the results in the sequence. I will not prove them. It's not very difficult to prove, actually. I mean, if you have the interval 0, 1 here, we have something like this. Here is 2 epsilon alpha L, 3, and so on. And so this distance here is something of order epsilon alpha. This outside will somehow be cancelled by this one, and it will remain this part that will go to 0. Formally, this is basically the justification that this will go to 0, okay? When you rigorously try to prove it's a little bit more. So one more remark is that when we start the proofs, we will basically consider this. So okay? We will basically be ignoring that zero order term. So we will be able to write it like this, just to simplify notations and not to be have very long expressions. So let's state some results and definitions regarding definition 3. So a sequence phi epsilon in L1 of R epsilon satisfies the unfolding criterion for integrals, for short UCI, if this integration defect goes to 0. So basically, if the sequence satisfies UCI, we will have that once we have the limit of this, we have the limit of this. So it's a very important property. Now I will state the sequence of results that somehow we will apply, okay? So proposition 4, so the first one, if phi epsilon is in LP of R epsilon with P between 1 and infinity, and the triple bracket norm of phi epsilon in LP is uniformly bounded, so okay, then phi epsilon satisfies UCI. This is actually very easy to prove once you have the definition and this bound. You just have to use Holder's inequality. It's quite simple. Moreover, if you have a psi epsilon, let's say, in an LQ with also uniformly bounded, and 1 over P with R bigger than 1, then here I will use the same phi, okay? Then the product also satisfies UCI. Well, this makes a lot of sense because when we get variational formulation of differential equations, we have this kind of product, which means that we have a function and the test function in the variational formulation. So this is the most one of the most important properties. Also, if we have, let's say, here, I will get it like this because of the test functions in limit problems for the Poisson equation in this kind of thing domain, okay? We expect that in the limit we have ODEs in the interval, so the test functions should be in 0, 1. Here, P prime minus 1 is 1. Then phi epsilon phi also satisfies UCI. And finally, if psi is a function in the basic cell, and we define psi epsilon as this, here let me take periodic here. If we define psi epsilon like this, then the phi epsilon, so satisfies here. So basically, this ends with the problem with the integration defect. So we don't have to really worry about it. Just a comment is that if later we want to try to find rates of convergence, to determine the rate in which this will convert to zero will be very important. This is actually a project I'm working very slowly for some years. So if you want to see, I will pass the references later from this. So next, what we have to do? Once we establish that if somehow the functions here are bounded, this will converge to 0, we have next to determine the convergence properties of unfolded sequences. So that's what I will establish here. I will just put the results in sequence as, again, it's not very difficult once you get the definition of unfolding and get some basic results on functional analysis, but in any case, next we state some convergence properties of T epsilon. So what's the number? Okay. Proposition 5. If phi is a function in LP of 0, 1, then converges to phi strongly in LP. So, regarding test functions, as I was mentioning here, this is basically as important because the test functions will be somehow in a Sobolev of 0, 1. And then when we get the product of a test function like this and the sequence for solutions of PDEs, we will have something very good, which later will be a product between a strongly convergent sequence and a weakly convergent sequence. That will not be a big issue regarding functional analysis for us, because in classical methods, if you're not aware, the big problem is that usually you have a product of two weakly convergent sequences using Tortas method, extension operator, and so on. That's the main problem in classical methods. Here we won't have this kind of problem because of these good, strong convergence properties. So, okay. Next, I will state one more essential convergence properties. So, let phi epsilon be a Sobolev sequence in epsilon with this triple norm uniformly bounded, and P is here. Let G0 XS ds. Then there is such that we'll not need anything here, no. So then there is a unidimensional function here, such that V epsilon converges to phi weakly in W1P of 0, 1, and strongly, of course, in LP of 0, 1. In LP, this will converge strongly to 0, and the unfolded phi epsilon will converge strongly to phi in LP of 0, 1 to values in in this space. So the sequence of steps to prove it, basically we integrated this in 0, 1 in X, then we will fall in this uniformly boundedness for the original sequence. Since this will be a uniformly bounded sequence in W1P of 0, 1, then there is a function, there is this function here, such that this V epsilon will converge weakly in the Sobolev and strongly in the LP. This is a property of the Sobolev spaces. And so, basically, after this, we show that the phi epsilon minus V epsilon converge to 0 in some kind of norm like this. And then we have this. And with this property, together with this one, basically we can prove that the unfolded sequences will converge to the same function. This is the schedule to prove this result. It's not very difficult. And what's the beauty of this? If you look at this sequence, somehow, what happens? Notice that I will make a draw here. So, you'll have the minima, which will be something like this. Here is the epsilon g1, which is the maximum value. And of course, you have something like this, okay? Here is 1 and here is 0. Basically, what is that V epsilon is telling us is that if we get a function that, let's say, formally, that somehow is defined just on the thin part, excluding this oscillating behavior in the upper part of the domain, the limit functions from this fixed thin domain, let's say, not fixed, but standard thin domain, sorry, the limit of functions in this standard thin domain will be the same as the one with the oscillations. So this is a very good thing, because this makes our life exponentially easier, yeah? Actually, if you have locally periodic or even other structures that are non-periodic, this proof basically works. Of course, if this g function is bounded by g0 up below and g1 above. So you can even have randomly oscillating boundaries for this result to work. This is very powerful. Okay. And finally, the last convergence result. I will state it in this middle part of the board. I will put it as a theorem. This is 6. Theorem 7. So, if we have with uniformly bounded with p between 1 and infinity, then there are phi here and phi 1 yes, in LP of 0 and 2 values. In the Sobolev such that up to a subsequence we will have so phi strongly in notice that this first convergence is from this proposition 6, okay? So basically proposition 6 is important to establish this. So, and we have now two cases. If the alpha here is equal to 1, then the unfolded gradient will converge weakly to the derivative of this phi plus so, and this is weakly in LP of 0, 1 times y star. Oh, squared, because it's and if alpha is less than 1, this derivative in the y2 variable is 0, and the unfolded weakly so this is a little bit more technical proof. You have to define somehow an auxiliary functional, in order to prove this convergence of gradients. And of course, we just have weak convergence. Later, as expected, when proving corrector results, we can establish that this kind of convergence can be strong, okay? And so this is basically the well-known corrector of the domain perturbation problem. Yep. So with these convergence properties in hand, now we can establish some rigorous results that I will be sketching at the very least in the sequence. Notice here that we just established the two cases that is the critical case and the weakly oscillating. And so in the critical, we have the influence of the derivatives in the oscillating part and as well the one regarding the compression of the domain. But in this one, when the boundary say oscillates more slowly, yes, then the domain compresses because this is less than 1. Then there is no basically influence of this vertical direction, which is the compression. So it somehow reminds the standard thin domain case, let's say. If we have enough time, I will try to prove the three cases, alpha equals 1, less than 1, and bigger than 1. I believe it will be possible, but... So, now, to prove our results, we will divide it in the three cases of oscillations, which is this one, and the bigger than 1. So, I will just state the theorem, and the next I will start the proof. So, here is 8. So, let U epsilon and H1 be the solution of I will rewrite it here to simplify of the Poisson equation, this reaction diffusion in R epsilon on the boundary. Here epsilon is positive and is more than 1. Here I will not say, but this is the classical normal derivate with uniformly bounded and such that the unfolded forcing term weakly converges to an f hat weakly in L2 of so then there are U in H1 of 0, 1 and U1 in in L2 of 0, 1, two values in H1 periodic such that this converges strongly in L2. Here, and the gradient, unfolded gradient will converge to this. Weakly in L2 of so if you see for now, basically if we have this uniform bounds of sequence, then we just apply this theorem here to obtain this part. It's quite simple. And U is the solution of minus Q UXX plus U equals to F bar in 0, 1 UX of 0 UX of 1 that is 0. This Q Y2 and X is the solution of the auxiliary problem. Here I will put in the weak formulation, okay? Of X. So the average of X in the cell is 0 and psi is here. So, okay. Basically, this is the main result. The most interesting case regarding homogenization. We capture the effects of the oscillation and as well the compression of the domain. And so we have next to make some proofs. I will make some remarks and then in the sequence I will start. Let's make a 5 to 10 minutes break because I don't want to keep it going for now, and then we do the proofs. I guess it will be something around 30 minutes of proofs in the worst case scenario, and that's it. So in 10 minutes we resume.